out. I'm very excited today to introduce Dr. Alice DuVivier from NCAR. Alice got her bachelor's in 2008 from Colorado College. From there, she went to the University of Colorado at Boulder, working with John Pisano on a variety of atmosphere and polar-related topics related to sea ice. You've been to Barrow, you've been to a bunch of different polar places. After that, she went to NCAR, worked as a postdoc with Bill Large on more ocean-related topics, ocean boundary layer, ocean coupling, mostly still in the Arctic. I assume Arctic polar locations. And then she transferred to the research track at NCAR as an associate scientist, and now as a project scientist 1, where she continues to work on all sorts of different sea ice and polar cryosphere topics. My favorite of which, of course, is this last summer when she calls me up about water mass transformation and its relation to sea ice. So that's definitely my favorite interaction with Alice so far. I really think she's, a great example of somebody who knows how to do coupled Earth system research with a polar flavor. There's not many folks who can work on both ocean, atmosphere, and sea ice all in one. So without further ado, take it away, Alice.
All right. Thank you. Can you guys hear me in the back without the mic? Is it okay online without the mic? Okay. Yeah. All right. So as Liz said, I'm Alice. Thank you for having me here. This is my first work trip since COVID, so it's really nice to see people in person and actually talk to lots of you. So I'm here, I'm going to talk today about one of the projects I'm working on. This one is in the Arctic. As Liz said, I do stuff in the Antarctic and stuff as well. I kind of go all around. And some of the people I'm working with are here at University of Wisconsin-Madison, so I just want to make sure everyone knows that science is really a team endeavor. At least that's been my experience and the way I like to do it. So I just want to acknowledge that. The other thing I wanted to point out, so I chose this picture here of the Arctic Ocean, and the main reason I chose it is I think it shows pretty well the topic I'm going to be discussing today, which is the changing surface sea ice, the changing surface of the Arctic Ocean, specifically sea ice. So you can see here, this is a sea ice flow in the middle. It's kind of rough and gnarly on the edges, and then this is probably really a melt pond here. These people are walking around it. But the ocean around it is relatively smooth compared to this. So this changing surface condition is what I'm going to talk about mostly today. So briefly, a map of today's talk. So this is not actually a map of today's talk. This is just a track from the 1893 Fram expedition. But what I'm going to talk about is about the changing Arctic. So this expedition happened, more than a century ago, but it's pretty similar to the Mosaic experiment that just went out, a couple of years ago in terms of its experimental design. But the Arctic has really changed a lot between, when Nansen was out here and when Nansen was out here and then when the Mosaic went out. So the first thing I'm going to talk about is kind of how the Arctic's changing. I'm not sure all of you are Arctic polar people, so I want to go into specifically how the sea ice and the winds are changing. Then I'm going to talk some about coupled model experiments, the ones that I'm using, some of the results we have, and then of course the conclusions. All right, so when you think of the Arctic, if I said think about the Arctic right now, my guess is that many of you would think of something like this picture right here, maybe this one down here. Lots of snow, lots of ice, it's very white, maybe a little bit of blues in there. And I want to point out that something that's unique to the Arctic Ocean that I'll talk about a lot is the sea ice cover. And again, I'm not sure how many of you think about sea ice, so I just wanted to point out, as a reminder so we're all on the same page, the sea ice is frozen ocean water, so it's a little bit saline. That affects how it behaves and moves and changes. And I also want to point out it's also pretty heterogeneous. You can see here in this picture, we have a bunch of melt ponds. So you have snow, you have melt ponds, sometimes you have bare ice. Those things can be weirdly distributed all around, or differently distributed, I should say. And so it makes sea ice kind of like complex to understand. You can imagine the roughness is also, in reality, pretty different from place to place, potentially. All right, so what's happening to sea ice and what's happened over the past 30 years? I just want to take a couple minutes to watch this animation that NASA put together about the changing ice. Before I start it, I just want to point out the scale up here in the upper right is the sea ice age. This is kind of a proxy for sea ice thickness. So the white colors are very old, thick, multi-year ice, and the grayer colors are the thinner, first-year ice. So we're going to start this. So this starts in the 1980s. It's going to go up to 2019. And I just want to point out, you can see the ice moving, what kind of the standard conditions were. You can see it moving around here in the Beaufort Gyre. You can also see it being exported through Fran Strait. Those are all totally normal sea ice motions. You can also see the annual cycle. So you can see it's growing at its max, and then it shrinks back towards the central Arctic and grows again. This is just what happens every year. All of that's normal. Just kind of look at how much of the Arctic is covered by this thick old ice in the early 1990s. All right, you can already see some changes starting, but we're about to get into the 2000s, and this is when the changing sea ice really kind of took off. Still see the annual cycle where the sea ice expands pretty widely every year and shrinks back. And we're getting towards 2007, which is one of the first banner years of major ice loss. So just be quiet and let that go by. So you saw there was a big inward shrinking of that ice cover. We're getting to 2010. There'll be another. I want you to pay attention to 2012 as well, when the minimum extent of sea ice occurred. All right, so you can see now it's going to keep playing. We'll see this same cycle go on until 2019. But you've probably already noticed that there's been a huge change in what the sea ice looks like in terms of its state in the central Arctic. So that's the end of this animation. If you look at what the sea ice looks like kind of now, this is close to present day, this thick ice is really only present now at the northern Canadian Arctic archipelago. And this is at the minimum, but we started off with this thick sea ice pretty much in the whole Beaufort Sea part of the Arctic Ocean. So there's been this massive change. This is what it looked like at the start. All right, so what is sea ice? I just want to give you a sense of the mean state, kind of how sea ice behaves. So the Arctic sea ice volume is decreasing. Part of this is due to the spatial coverage of the ice decreasing. So if you look down on it from a satellite, that's what we're seeing here. You see the annual cycle, we get an increase in March, and then it decreases, and you get a minimum in September, and it increases again. So even though the ice has changed, we still have a pretty big seasonal cycle. We're still getting pretty rapid expansion, but I do want to point out, even in March, at the maximum, we have less sea ice extent than we did a while ago. And these purples and magenta colors are the past decade. You can see they're well below the median in all months. And then the aerial extent decrease is really the largest in September when we reach the minimum. Oh, and then 2022 is one of these purple lines that's right here, but this coloring, you can actually see the difference. All right, the other reason that the ice volume is decreasing is because the thickness itself is shrinking. We saw that really well in that animation. So we're both getting spatial extent decreasing and the thickness decreasing. And so the overall volume itself is decreasing dramatically. And ultimately, what this suggests is that the ice is going to become more seasonal rather than perennial in the Arctic. So before we talk more about the future, I just want to talk a little bit about what's happening right now, because I don't always pay attention to this day to day. I don't know if any of you do, but we're kind of in some record situations right now. So March 19th, which was just a couple weeks ago, both polar regions were breaking records, which is kind of unique because it was happening at the same time for both, so there was a lot of media coverage about this. And in the Arctic specifically, there were some individual point locations that were like 50 degrees Fahrenheit above the average conditions, which is kind of huge. And then the Arctic as a whole, as you can kind of see in this figure, kind of horrible color bar, I'm sorry I didn't make it, that the whole Arctic was about 6 degrees Fahrenheit above average. So it's really warm in the Arctic right now when it's like the middle of winter. And at the same time, we're also seeing some kind of unique situations with the sea ice right now. So this is the 2022 sea ice extent in blue. And we actually reached our maximum this year on February 25th, which is really early. You can see here, these are the 10 lowest maximum sea ice extents. So we're the 10th lowest on record, but we have one of the earliest melt dates. And why that's potentially concerning is that basically we're starting melt, in some cases, a whole month earlier than maybe the maximum would have been, and so, that's a whole bunch of more melt that we're likely to have this year. The other thing to point out is that we're actually kind of getting just a little bit of melt now in March, so there's melt at both poles, because of course the Antarctic is experiencing summer right now, we'll go into the fall. And so, this is really, something to note. I think it's a specific weather event. It's not necessarily going to say, we're going to get the lowest Arctic sea ice extent on record this year. Because of this, there's a lot of variability in the ice and what will happen over the summer, but it's definitely something to point out. And the other thing I want to point out is that the system's really coupled. So we're getting melt in March of the sea ice, and we're also getting extreme Arctic temperatures, but those things are influencing each other. So the extreme temperatures can be helping melt some of the ice, but as you melt ice, you expose the relatively warm ocean below. You can also get energy input into the atmosphere, which helps warm it up too. So this coupled system is pretty complex and interesting. I'm going to talk a lot about that in the rest of the talk. Oh, I also want to point out that the Arctic sea ice minimum is happening right now because it's their summer. And for the first time in the satellite record, the ice has dropped below 2 million square kilometers, so they're also making a record this year in terms of the minimum. All right, so I want to talk a little bit about climate models. What I'm showing here is an old climate model. This is from 1980, well before I was born. This is a pretty classic paper by Gnavi and Stoker. But what I'm showing here is the temperature increase from that the model is projecting with quadruple CO2. And the important thing to note here, might be hard to see, is that in the Arctic, what they found was that the temperatures were going to increase a lot more than they were in the equatorial regions. So 2.5 degrees in the equatorial regions, but like 8.75 degrees in the polar regions. And so this more dramatic positive temperature increase in the Arctic is known as Arctic amplification. Maybe you guys already know this, but I want to make sure that we're on the same page, and we've actually observed this. So I think what's relevant about this, especially if you don't work with climate models a lot, is to point out that climate models, decades ago were projecting things that we've seen today. So they're really capturing the essence of the system. Even back in 1980, they could capture some of what was going on in the real Earth atmosphere system. And we have more complicated models now that we can understand more of the details of what's happening, or more complex processes, and I'll talk about using one of those models in more detail. All right. So how is the Arctic going to change in the future? If you look at this picture, your first thought might be that this is photoshopped, but it's not. So it's from 2019 near Greenland, and what you're seeing is essentially one giant melt pond over like all of the sea ice near Greenland, so the dogs aren't just walking on water. They're actually on ice below that. But this gives you a sense of this fundamental shift that's happening in the Arctic. If you think back to that first picture I showed with the sled dogs on the snow, this is kind of what we're going towards. It's really, really different. All right, so what do climate models project might be happening? So one of the things that is changing is that the Arctic is shifting to being more open ocean. So this figure right here is showing the number of ice-free days per year. White colors indicate basically no open water, and the darker colors indicate more open water per year, so days per year. And what you can see is that using climate models, if you look at the 2000s all the way to 2100, there are some locations, you can think about here in the Beaufort Sea, that are going from being essentially ice-covered year-round to ice-free year-round. So many locations around the Arctic are going to experience more open water every year. And sometime in the coming decades, maybe in the 2030s or 40s potentially, the Arctic is likely to go ice-free in September, which we usually take, I put this in the wrong spot, it should be 1 million square kilometers, and the ice area drops below that. So this means that during the summer, basically there won't be ice covering almost the entire Arctic except for this little area, the last ice area north of the archipelago. So we're having this big shift over the Arctic Ocean to being more and more open ocean. At the same time, what we're seeing is that it's likely that near surface winds will increase. So this is work by Steve, who's over here in the corner. But what we see here is that in winter and autumn specifically, it's likely that in the future it'll be more windy, which is shown by these red colors, over the Arctic Ocean. We see the same in spring and summer, though the signal's not as large, and potentially even over land a little bit in these same areas. So we're going to get more open ocean. We're likely to have stronger near surface winds. And these changing winds seem to be associated primarily with changing sea ice rather than, say, changing pressure gradients and stuff like that. All right, so why does this matter? Why do we care that these things are changing? So I'm going to talk just a little bit about how the open ocean and the wind are connected. So when you have wind that blows over the water, it creates waves. And when you have lots of wide open ocean, you have what's called more fetch. And so you're going to get larger and larger waves over time. This monster wave right here. So this is really relevant in the Arctic because a lot of the coastal communities are experiencing pretty dramatic coastal erosion. So you can see here in this picture from the National Snow and Ice Data Center that whole coastlines up to buildings and infrastructure are being eroded. There are also impacts of archaeological sites in these areas, as well as, of course, the biology and ecology in the region too. So some of these communities are facing kind of existential questions about if they should stay in the coastal location they are, or if they should maybe move. And the reason that this is really relevant is that they no longer have sea ice along the coast, especially in the fall and stuff like that, when there are storms, and the sea ice would have protected them from some of these big waves. But when we get stronger winds, more open ocean, the coasts are more exposed to these large waves. All right, there's also likely some impacts on vessel traffic. So as the Arctic becomes more ice-free, it's projected that there are going to be more and more ships entering this area. And when you have big waves due to stronger winds, you also set up conditions where you can have accidents with your ships. And so this is from 2019. This cruise ship near Norway got kind of stuck in a storm with really large waves, strong wind conditions, and they had to get a bunch of helicopter rides to evacuate all the passengers. So things like this might occur more in the future. So I talked a lot about how the wind impacts the surface, but it's a coupled system. So the surfaces are also impacting the wind, the changes in the wind. All right, so this figure is one I found about wind energy production, but there wasn't anything for sea ice the same way. But what I want to point out is when you have a wind profile like you have here over the open ocean, if the surface is relatively smooth, you're going to have pretty strong winds near the surface. So this is like open ocean conditions. In contrast over sea ice, which of course this is more exaggerated, but sea ice, it's a lot rougher over sea ice, and so the near surface winds are going to be lower just because you get that turbulence, some of that momentum from the atmosphere as a part of the sea ice moves around. And so those near surface winds are responding to whatever the surface type is as well. I also want to point out that the open ocean roughness is wind speed dependent, so it's not like a constant, it's always nice and glassy, but it is in generally speaking, it's less rough than the sea ice. All right, so we have some science questions based on these projected changes. We want to understand how changing surface roughness due to changing ice cover is going to impact both the sea ice and the atmosphere. We want to understand how this might shift the mean states of each of those components. We also think that it's likely that the changing roughness might impact the processes or feedbacks between these two couple components. And we're also curious about what sort of regional or seasonal differences emerge.
Alice, is there a threshold wind speed over the open ocean with ice adjacent where there is no difference? Because I'm imagining if the waves are big enough, then your obstacles on the open ocean are the same as they are on the ice or even greater.
Yeah, I think probably in reality there is. In climate models, a lot of times, because there aren't good observations in like super windy conditions, the parameterizations are not as good.
Oh, okay.
And so there's usually like kind of a threshold wind speed where they don't know that it's just like the same roughness.
Okay.
And you also get things like the waves themselves are like kind of blown off, and so that really affects how you define roughness too. So I think the answer is yes, probably, but it's not necessarily in the super stormiest conditions accounted for because we don't have good observations.
Okay,
in
yeah,
those
thanks.
conditions. All right, so the Arctic's changing. I'm going to talk now about the experiments that we ran and what they're showing us. So I believe a lot of you are observationalists, so I just want to make sure we're on the same page about the coupled Earth system model. So I work with the coupled Earth system model, or CESM, which is developed at NCAR and by the community at large. It has a number of different components, so I'm mainly going to talk about the atmosphere and sea ice, but I also want to point out that there's land ice, an ocean model, runoff, land itself. So there's a whole bunch of these different components that are all evolving together in time to give us some of these climate projections. All right, the main tool I'm going to be using is the CESM2, so this is the CESM version 2 large ensemble, which is freely available to any of you if you're excited about working with model data. I just want to describe what this is like a little bit. So we run a pre-industrial control with our coupled model so that we can know that it's well equilibrated, the ice and the ocean are not drifting a lot, stuff like that. And what we do is after this pre-industrial control, we choose a number of initial conditions. So these four that it's showing are 4 different ocean states that they were chose specifically. And then we're going to initialize some historical and then future experiments from those. So each one of these 4 conditions, we then have what are called micro ensemble members. So we give the atmosphere a round-off level temperature difference. That's little 10 to the minus 14 Kelvin differences, something so small we couldn't measure that difference. And then you let the climate model run. Because of internal climate variability, these ensemble members start evolving differently over time, and you get slightly different, weather patterns and stuff like that, but it gives you a range of what the likely climate states would be in the future. So the CESM2 is just some basics of information about it. It's nominal 1 degree forcing. What I'm using is just the CMIP6 standard forcing. There's some details in how this is done, but half of the ensemble uses the standard forcing. That's what I'm using. So there are 50 ensemble members total. The combination of these micro perturbations, this round-off level atmospheric forcing, and then the macro states, the different ocean conditions, allow us to really capture this full range of variability. And just so that you can see what this looks like, this is the surface temperature anomaly. This is global. So the red is observations, and then what you see here is the ensemble mean from the large ensemble, and the gray is kind of the range of what all the different ensemble members show. And we can see a similar thing. I'm just going to point out the Arctic sea ice extent anomaly here. So you can see the ensemble mean and then the observations. So they're relatively good. What we want to see with this is that the observations fall within that range of model possible climate states. They're not expected to agree exactly. That's not how climate models work. We're not replicating the past precisely, but we do want to see that it is reasonable for what we actually saw that climate exists within that range. And then what we did was we ran some perturbation experiments in which we artificially smoothed the sea ice roughness to be equal to what it is in the open ocean, so this is wind dependent. So you can see here in the regular CESM2 large ensemble, the 50 numbers, the ice is relatively rough compared to what it is in these smooth experiments, which is called smooth. And why this is really relevant is we have 5 ensemble members. That's not enough to capture a full range of climate variability, but it is enough when we compare to the CESM2 large ensemble to see, are there statistically meaningful differences between experiments. And the whole idea is to use this to understand how is the changing roughness specifically impacting the changing ice or the changing winds. Like, is there an impact with the roughness itself? And the smooth experiment, I will say, I'm just going to show you things from about 2020 to 2100, so just the future experiments, but we did do a spin-up for this as well to make sure it wasn't drifting. All right, so what are some of the results we're seeing? All right, so the first thing to point out, I'm going to show a number of these plots, and I just want to make sure that we're on the same pages. The dark blue is the ensemble mean for the smooth experiment in all of these. So there are 5 members. The dark black line is the ensemble mean for the CESM2 large ensemble with all 50 ensemble members. And then the gray lines behind are bootstrapped means from the large ensemble. So using 5 members, we've done this 1,000 times to kind of get the sense of what would the mean be if we just took random groups of those 5. So that kind of gives you the range of variability there. So when we look at the sea ice extent over just the central Arctic, which I'm pointing out to be here in the bottom right, the big takeaway here is that the sea ice cover in all seasons is not really affected by the changing roughness. The mean state is really not that different, which is kind of good in a way, because then we can see how other changes or feedbacks might change when we know that the ice itself is relatively similar. And this is just the annual cycle, like I showed before. The statistically different months are in the bigger circles, so you can see that almost no months in the decades, the 2020, 2040s, 2060s, or 2080s are very, very different. Though I will point out that there's, in general, in the later decades, the smooth model does have slightly more sea ice area, but it's not statistically significant. All right, but when we look at the wind speeds, we do see that there are statistically significant differences here between the two experiments. So what I'm showing here is autumn, winter, spring, and summer. And in all of these, in the first three panels, you can see that the smooth ensemble mean is significantly higher than the CESM2 large ensemble. So what this is telling us is that in the smooth experiment, when we have a nice smooth surface, the wind speeds themselves end up being higher, the 10-meter wind speeds. The only season where this is not the case is summer, which actually makes a lot of sense because we're melting a lot of the ice. There's a lot more open ocean, and so those speeds are a lot more similar. You can also see that the rate, the trends, which are given by these dotted lines, there are some differences, especially in autumn, but maybe also in winter, in how these are changing over time. So you can clearly see the increase in time, as Steve was pointing out with his plots, in autumn and winter. It's a little bit less clear what's happening in spring and summer if you're looking for the whole forward path. All right, so now what I'm showing you are the ice loss trends in both experiments. So this is the ice concentration on the top row, the ice thickness on the bottom. For both experiments, we see, as we saw, the mean state was really not that different. So unsurprisingly, the ice trend, the ice loss trends, which are negative everywhere when we're using concentration and thickness, are not hugely different. Though I do want to point out when we look at the differences, these are percent differences for CESM2 large ensemble. In the Siberian sector, we do see that there are differences that are on the order of like 10 to 30% different. And I'm just showing autumn. It's relatively similar for winter months, and it's really not, there are a lot of, there are not very many differences in the trends in spring and summer. So I'm just not showing those here. All right, when we look now at the trends in the wind, what we see is that in autumn and then in winter, both sets of experiments show this increasing wind. So that's the red everywhere, that's showing increasing wind speed over time. But I also want to point out before I talk about the differences that the pattern of the trends look pretty similar to the ice concentration trends. So that lets you know that it's very likely that there's a strong relationship between these two. All right, so this is the same as before, just now with the difference panel. And what I want to point out is that the trend difference is pretty large between the two. So in autumn specifically, losing that change in roughness over time means that the wind speed trends are about 30 to maybe 60% smaller than they were in the CESM2 large ensemble. And we see similar decreases in the trends in winter, though they're not as large. So what this tells us is the changing surface condition itself is actually really important for setting the trend, the magnitudes of the trend in the wind speed changes, but they're not the only thing driving it. There's probably something else driving it, which we think is likely the near surface stability, but it is pretty important. All right. So I've talked now about the mean state and those trends. Let's talk a little bit about the processes and the feedbacks that these All right. So I'm going to specifically focus on freeze-up processes, so in the autumn and winter, and I'm going to look a lot at the Siberian sector because that was the only sector where we really saw big trends or big differences in the ice loss trends. So first I'll talk about the sea ice, that's why it has all the stars. And I want you to remember that the near surface winds were uniformly higher and smooth than they were in the large ensemble for these specific months. And this is due to less momentum loss to the surface. All right, this is really hard to see with these colors, so I'm sorry. But one of the things we find is that when we look at the ice speed, this is an annual mean now. In both experiments, we have our Beaufort gyre here, the cyclonic motion, and then the transport drift export through the Arctic. That's in both experiments. But when we look at the difference here, you can see that the ice speeds themselves are a lot slower in the smooth experiment. So the blue colors here are slower, and if you look at the vectors, it's like opposite of the Beaufort gyre, so it's just like a slowing down of that circulation. If you just look at the scalar ice speed averaged over the whole central Arctic, you can see that's uniformly lower too. So we had stronger winds, but now we see much slower ice speeds. But does this make a difference for transport in and out of the Arctic? The answer is basically no. So we looked at ice fluxes into the Arctic through the Bering Strait, which I'm showing here. Positive means gaining ice so into the Arctic. And then fluxes out of the Arctic through the France Strait and the Bering Strait down here along those lines. And what you can see is that the ice loss through these two flux gates is decreasing over time, mainly because ice itself is getting lost over time. Same with ice inflow into the Arctic, but the ensemble means are really not different. So the ice speeds change a lot, but we're not really affecting the transport through the Arctic, which is good because we found that the mean state was different. So if this was really different, that would potentially be concerning. So what's going on? So what we think is happening here is basically when you have this smooth experiment with the sea ice that's essentially open ocean, you get a decrease in the momentum transfer from the atmosphere to the ocean. So that's why those wind speeds are a lot higher. It also means that the ice speeds are going to be a lot lower. It's not being pushed as strongly by the winds blowing. The converse, of course, is true for the large ensemble. The momentum transfer is going to be higher because you have that stronger coupling due to that rough surface. So, as I pointed out, this isn't necessarily something that's going to be important in all seasons or in all regions. So, we're really focusing on what seasons or regions might this be relevant. And can this momentum flux shift maybe explain this difference in ice loss trends? So this is why we're focusing on the Siberian Sector specifically. I also want to point out, this is going to be almost impossible for you guys to see in the colors, I'm so sorry, but the Siberian Sector right here, this is an area I'm going to just like follow the arrows, but it's an area where you're basically losing ice a lot of the year. So we're getting ice that's transported away, that's what these vectors are showing. So I think of this area as kind of like an ice nursery. So in the summer, when the pack melts back to the central Arctic, this area often becomes kind of ice-free, and then it grows again in the winter. But that ice is then ejected into the rest of the pack, and it kind of is a place where ice forms repeatedly over the whole winter. So that's what I mean as an ice nursery. So one of the nice things about climate models is you can kind of break down the different processes you're getting and how those affect the different components. So what I'm showing you here are the tendencies for the ice concentration, so how they change in time. The total tendency for the ice concentration here is in black. The thermodynamic contribution is in blue. The dynamic contribution is in red. I'm just showing you autumn and winter. And then the solid lines are CESN2, large ensemble, and the dashed lines are smooth. So the first thing that jumps out to me is that in both of these seasons, in the smooth experiment, we have a smaller magnitude dynamics trend. So basically the negative here means that, oh, and I should point out we're just looking at the Siberian sector here, we're average over that. So we're basically getting less ice loss in the Siberian sector in these smooth experiments. So those ice speeds are lower, we're not blowing ice away as quickly. At the same time, we also get a smaller magnitude thermodynamic gain in this area during the freeze-up period. And the combination is basically but they compensate, and so we don't get a big change in the overall tendency. Though I will point out, after about 2060, we see a little bit of an increase here, though it's not dramatic. So in this specific sector, and I want to say too, I'm not exactly sure what shifts after 2060. That happens to be where it's likely that the Arctic Ocean is going ice-free, so it might have something to do with that transition period, but I'm not really sure yet. So that's, I think there's always questions you're going to have about everything that comes up. And I think there are some questions too about some of the internal variability. So we only have 5 ensemble members for the smooth experiments, but maybe if we had more, we'd see that some of that variability decreased too.
But wouldn't that be consistent, your idea that the Arctic's actually ice-free at 2060, wouldn't that be consistent with the fact that the dynamics contribution is no longer different?
Yeah.
Because the whole ocean's smooth now.
Right.
Right?
So, yeah.
But the thermodynamic contribution kind of switches sides.
Yeah.
Yeah, so that's what I mean by the internal variability question. So we don't have enough ensemble members, I think, to know for certain what's happening there, but I think that the first key is kind of, okay, we see that there is a little bit of a shift around there. And it's really a regional and seasonal specific shift here.
What are the time scales for the internal variability for ice?
Do you mean like what's kind
Like,
of
you know, atmosphere, you think about decadal time scales.
Yeah, it's more I would say it's like more decadal variability. It's not as much in our annual, the ice memory is usually longer, though as you go towards an ice-free Arctic Ocean, it's going to decrease because you're essentially melting all of that, so you're regrowing and starting from scratch every year. So I would say that it's kind of shifting in time too. All right, so the main thing I think we're showing here with the contrast between these two experiments is that this changing ice surface specifically is relevant for this kind of feedback that we see here. So you get this greenhouse gas forced temperature increase. As a whole, this is going to decrease your ice area. As you decrease your ice area, you're going to decrease surface roughness, getting more open ocean. That's going to decrease your momentum flux coupling, which decreases your ice transport. This is all kind of on a local scale. And at least in the Siberian sector, this leads to a slight, I don't want to say increase in ice area, but less rapid loss of the ice itself. So it's still a negative trend, it's just not as strong as a negative trend. But this is really you're really only seeing this impacting the Siberian sector because it's that ice nursery location. And it's really only during freeze up because that's when we're really growing ice and this is the most relevant time of year for this process. All right, so then what's happening in the atmosphere? So now we're going to look just briefly at the atmosphere. All right, so one of the things we see in the atmosphere is that if we look at the planetary boundary layer, which here, this is the trend in the planetary boundary layer height. It's red everywhere, which means it's increasing everywhere. So basically that suggests to me that we're getting an influx of energy into the atmosphere, as you would expect when you're losing sea ice. And again, this is autumn, so sorry I didn't say that on this slide. But where we're seeing the difference in this trend is also in the Siberian sector where that ice difference is largest. And at least some preliminary indications suggest it has to do with the turbulent heat flux differences between the two experiments. So when you don't have that changing ice roughness, we're getting less energy flux into the atmosphere here because you're not losing the ice specifically. And there probably are some impacts as well with the fluxes themselves because the roughness is relevant for the ice flux, or for the turbulent fluxes. All right, so overall, the main thing I wanted to get across is that without this change in surface roughness, we find that the momentum transfer between the atmosphere and the ice and ocean has decreased, so that leads to the faster winds, the slower ice speeds, and it affects the trends of the winds most intensively, and that you get local processes related to the ice dynamics that change during freeze-up specifically. All right, so I just want to, we're kind of at the conclusions part of this talk. I just wanted to say too that I included this zoomed in map of the Fram track because I want to point out that sometimes research is just like this track where you're kind of going in circles or you're not sure where you're going to end up. So it's a little bit wonky there. not linear at all. All right, so the first conclusion here is that the decreasing surface roughness is a significant contribution to that increasing autumn and winter surface wind speed trend. Without having that change in roughness, we still get increasing winds, but they're not nearly as large a trend. We also see that when we don't have the changing surface roughness, we weaken the, getting rid of that basically weakens these momentum fluxes between the surface and the atmosphere. And this leads to lower sea ice speed and transport. But ultimately, the only place that this changing momentum flux coupling impacts the ice is in the Siberian sector during freeze-up, where we just get less rapid loss because of special kind of ice inertia status. Right. So I think that's all I have. I'm happy to talk about any of this in more detail, but thank you for listening.
We get a student question first. Evan.
I just want to make sure I'm understanding this right. In reality, is younger ice smoother than old ice? Okay.
Yes.
And so you made all of the ice the same amount of smoothness. Is that
We said anywhere where there's ice, it will be the smoothness that the open ocean will have. So there is
Okay.
wind speed dependence in there, but
Oh,
it's not,
okay.
yeah, so it's not a constant. We didn't say it's just a constant.
okay? And one other question I had about the model is there any roughness change from like convergence of ice? Like I imagine if you have ice all coming into the same place, that it would like get a lot rougher. Is that represented at all in the models?
That is true in reality. It is not true in the models. There are slight changes in the ice roughness that are mostly related to like the ice state itself, so what the concentration and thickness are, but not, when you get convergence, you don't make it a lot rougher, which would be nice to have, but it's, yeah, that's one of the downsides of models, right? A little bit simplified.
Yeah.
Yeah, I just have something related to that, that with melt ponds, presumably that would also increase the roughness. I know we have melt ponds in CSM too, but does that actually decrease the roughness, or are they just kind of their own thing that we deal with right now?
So right now, the melt ponds in CESM2, we have melt ponds, but they only affect the albedo. They
Yeah.
don't affect the roughness or anything like that. And I was actually talking to one of you who I can't tell who everyone is with mask now. But in terms of precipitation, the melt ponds are also, like when it precipitates, that doesn't affect the melt pond. So we don't like freeze over the top of the melt pond if it gets cold. And those are things that I know are being developed right now, specifically from the mosaic observations. They're looking a lot at like how should snow and melt ponds and stuff like that evolve in the model, but it's still, I mean, it's good we have them at all, but it's definitely still relatively rudimentary.
Right. Do you think they would make a significant contribution to changes in roughness, or do you think like getting rid of the ice is probably the bigger piece of this so far? I guess it just depends, right?
I mean, in the Arctic in the summer, you get points where it's like tons of melt ponds everywhere, so I would think that at some point, once the snow is mostly melted off the surface, but the ice itself is maybe not gone, the roughness might decrease dramatically, but I don't know that anybody's studied that or even looked at it with observations.
Thanks for the talk. I had a question about how different is in the winter Arctic Ocean surface temperatures from sea ice temperatures. And the reason I ask is because wind speed gradients, your study focused on roughness, but are also driven by thermal, like which changes the stability of the atmosphere above. And
Right.
I've done some studies in the Great Lakes showing that that's an important contributor to wind speed differences at the surface. I'm just curious, because in your experiment, right, you can only change the roughness, so you didn't have a temperature change. But I don't know how different the temperatures are. Whether
So I
it
mean,
matters.
at the base of the sea ice, the temperature is roughly negative 1.8 Celsius, right? I mean, there'll be a little bit salinity
Sure.
dependent there.
Okay.
And then we do model the temperature profile through the ice, but it'll depend, what that surface temperature itself is, will depend on what the atmosphere is and those fluxes. So I would say some of those processes are considered, like we do actively
Yeah.
model that the temperature gradient and therefore the fluxes through the ice, but yeah, I'm not sure.
Okay. Yeah, I mean, I think it would run in the opposite direction, because if ocean water is warmer, then that would increase instability, which would then lead to more mixing of winds and a steeper profile near the surface. But
Yeah.
I have to think about that, but there could be something there too.
Yeah.
Oh, sorry.
Oh, go ahead.
Alice, thank you for your talk, super interesting. I wanted to ask you, as sea ice progresses into new ice, right? Obviously, multi-year sea ice is more rough, and we know that 2050 we'll probably see new ice every year, that's multi-year sea ice. My question is the model also considering the roughness changes over time based on multi-year sea ice laws, or?
So like, does the model know that you have multi-year ice versus first-year ice? Is that what you mean?
And like, does it account for decreasing of roughness? Usually multi-year sea ice is
Yeah,
super rough.
nice. You've got lots of convergence. It's all gnarly. Yes and no. I guess in the model, when you have multi-year sea ice, it does track ice age. So you look at 1+ years old. The concentrations and thicknesses tend to be higher, and so that'll affect the model roughness. But it's not. And you do have a fraction of deformed ice, but the fraction of deformed ice doesn't tell you specifically what the roughness would be for itself. So, kind of, but not entirely.
The idea of an ice nursery in the Siberian region is really interesting to me. So I have two questions. In the real world, is that pulsating during the early onset of winter, late fall into the winter, so that you have periods of time where ice forms, then it's exported, it's open again, and you do it again? And then does the model mimic that if it does happen in nature?
I don't know that people have looked in the model. I mean, I think you do have events where, like, you have open ocean, and there's a storm or whatever, the temperatures decrease, and then suddenly, like, ice forms in a big area.
Yeah.
And then, depending what the specific weather is, you get export or, like, convergence of that, and so it'll change the ice edge. I don't know that it's always, like, super periodic.
Okay.
Not the same way, so like I think a lot about the Antarctic too, and I think of Plinius as like the ice nurseries of the Antarctic, and those are more periodic. Like in the Antarctic, along the coast, when you have a strong downslope wind event, it pushes, ice away from the coast, you get ice forming, you push more ice from the coast, and that is very periodic. But I think in this area, it's a wide enough area that I'm not sure you would see like the whole Siberian sector freezes at once, but I do think you see kind of like when a storm passes, like I said, you'll get a big area that freezes. And that actually happened this last year in the Arctic. It was really warm, and then a storm came by and it got cold, and then suddenly like the ice froze in the northern sea route, and a whole bunch of ships got stuck and had to be rescued by the Russian Coast Guard equivalent, what that is. And so I do think it can kind of take people by surprise, and I think a lot of whether it freezes quickly or not also probably has to do with like the local ocean heat content.
Yeah.
So if the ocean's warm enough, even if the atmosphere itself is really cold, you just haven't lost enough energy from the ocean yet to freeze a large area.
Has anybody studied lake effect snow along the north coast of Russia?
I don't know. I don't know
Because that would
Russia
be
will
really
let us
interesting. I mean,
know.
that would give you some idea about the periodicity if there is such a thing.
Yeah.
You'd think.
I don't know.
That'd be interesting. Okay, thank you.
Kyle.
Yeah, thanks for the great talk. I was wondering about, so I don't know too much about this, but I know at least at times you get like a barrier jet that forms along the sea ice edge, jet that forms along the sea ice edge. I was just wondering if you thought about that at all in terms of does the change in roughness affects, that phenomenon and that maybe play into some of your results?
I haven't studied that specifically, though I did know that that sort of thing happens, the barrier jet with one ice edge. My understanding was that was maybe more due to the baroclinicity of like the ocean and the ice, not necessarily roughness, but it's possible that roughness would play into that. I think to really study that well, you probably need a higher resolution model than CESM here. So this is like nominally 1 degree, so it's a pretty low resolution model, but if you had a higher resolution model, I think you could get some of the detail of the ice edge, and I think the challenge is I'm trying to think if I know any model that does that. NOAA has like a forecast model, we used it for Mosaic, that might be the best option, because it also has active sea ice. And most forecast models I don't think have active sea ice that I'm aware of. So.
I'll ask some questions about the capital high resolution models. Are you, like, how familiar are you with that, those results? Like, are high resolution coupled models having different trends, different regional changes than the CPEP class models, or is that just still out there yet?
Yes. So the high resolution models, a lot of times I think what happens with climate models is you go to a higher resolution, maybe like some new atmospheric process is resolved better, and then that reveals some sort of bias that was in the model to begin with that now is no longer compensated for, and so then you're like, oh, we lost all the sea ice, or like, oh, we have really thick sea ice, what happened? And so the other issue, I guess, with this sort of study with high resolution is you don't, because they're so expensive to run and tune, you often don't have multiple ensemble members, so it's a little bit of like a different beast to look at. I feel like it's not that the processes themselves are different, but you do start to see some of those like shifts in what the dominant process can be based on like what is now resolved, or like the importance of eddies in the ocean or something now become relevant, and suddenly like you're fluxing a lot more heat into the Arctic and all your ice melts or something like that. So I haven't worked a whole lot with the super high resolution models, partly because of those challenges with tuning them again, I guess, but that's on the to-do list, I guess.
So a lot of what you looked at was ice atmosphere coupling. I was wondering what the reduced momentum flux does to the ocean, so like the ice and ocean coupling. And then also whether or not the increased wind but still over ice is different than increased wind over open ocean, like what those differences are.
I have not looked at the ocean momentum flux in detail, so I don't know the answer to that one. I would guess it would also be reduced because like the wind blows the ice and then the ice transports some lower momentum there. And then can you repeat the second part of the question? Sorry.
So if you have ice being advected over the ocean, or like reduced ice because you smoothed it, what does that look like compared to just wind over open ocean? Is there a difference?
Probably. I mean, I guess I'm looking at like means over time and space and all of that. So some of those detailed differences are probably smoothed out a little bit in all the averaging. So I guess maybe you want to look at like probably be more like daily scale stuff, which I looked at mostly monthly means here. So maybe, I don't know. That'd be interesting.
Okay.
Do you have any questions online? No. Any other questions?
I'll just, before we just conclude, just announce, of course, we have another talk next week, so please do come for the continuation of the CPEP seminar. Next week's talk is Nicole Ward, who is with the Minnesota DNR as a water resources ecologist, and it's going to be sticking with an aquatic theme, but moving to lakes, modeling lake ecosystem change and socio-environmental systems to improve water resource management. Thinking a little bit about some of the policy and management questions you might have with lakes around here. So stick around for that, and with that, I'll let you, I guess we should just give another hand to our speaker,
All right.
Out of town?
No.
Okay, that's what I was.
Yeah, so she's